context, we have traffic flow that necessarily then relates to how the information flows. Similarly, infection rate, there's a fixed infection rate for different diseases. In our context, that rate at which information propagates can change with basic density. And in terms of time resolution, typically they are not used in the order of seconds. And the objective for us is to manage propagation of information. So there are similarities that I talked about in the previous slide, which led us to use this analogy. But there are differences that then require us to see how we can leverage, but also make sure that it is consistent with what happens in the context of our system. So this is where we have a multi-hop information flow propagation. And what it says here is we are interested in information propagation, which is, what that simply means is, rather than information broadcasting, rather than unicasting means, we try to send the information out, in all that. In some sense, what we're saying is we're trying to just broadcast information, rather than looking at movement from one vehicle to the next. Okay? Because when you say one vehicle to the next, assuming that all of that is known, it requires you to know where the vehicles are. But there's from an application standpoint, this is important, especially when we're looking at safety applications. Because in safety applications, we want information to reach all possible vehicles as soon as possible. So you just blast the information out rather than do a unicast. So that's the difference. And this is the kernel function that I talked about previously. So this is simply illustrating what happens if you have a single hop of vehicles. And based on that, we have what is called this kernel function, which is K, and the infected vehicle rate, and then we have the susceptible vehicles. And this kind of gives us the ability to determine what is at the individual level. And then what we are interested in is multi-hop, which is what happens when there are multiple vehicles. And here beta is the communication frequency. And so that is the mechanism we use to determine how the information spreads continuously. So in some sense here, the single hop simply is illustrating what happens from vehicle to vehicle, but here is just talking about all the information seamlessly propagating. And this then becomes the equation that determines the movement of the information, which is from the spatial epidemic model. These are called integral differential equations. You can see that we are looking at, so what we are looking at here is the rate, the derivative s with respect to t simply says the rate at which susceptible vehicles change, and then the other one is just the mirror image of that, which is the rate at which vehicles get infected. So you'll see both of them are identical except for the sign. And this leads to a differential, which is an evolution equation, and that specifies how the system will evolve in time. The traffic flow model, this, many of you recognize that, the classical relationship between flow density and, here we have flow and the density, and you'll see that this is the fundamental relationship of traffic flow here. So with that, we look at the two closed form solutions. The first one, the closed form solution first, which is associated with the homogeneous traffic flow. And I'll first illustrate this and then show the case where we have the heterogeneous. So here, in the homogeneous case, what we are saying is there's uniform density. Okay? So the vehicles are equally placed in space. And in order to come up with the kernel function, recollect that the kernel function is the function that determines the probability of success. We have a function that here is the signal to interference and noise ratio, which comes from the domain of communication networks. And we look at different densities. In this study, we looked at a market penetration of 50%. We are actually doing the experiments related to other market penetrations. So you'll see that with different market penetrations, you'll have different outcomes. The other thing is typically the communication range, which means how far an information can go, is 500 meters, which means outside that cannot be transmitted. I mean, that comes directly from the constraints associated with communication. And what you see here is the equation associated with the interference. And all that is saying is that if this is greater than signal to interference ratio is greater than a certain threshold, the signal is strong enough for the communication to occur, otherwise the communication does not. So here you're starting to see the importance of interference, which is multiple vehicles are trying to communicate, and that's causing interference in the signal. So just because the signal is sent doesn't mean the other vehicle is going to actually be successful in capture. Okay? So that's the constraint that becomes particularly important. And using this concept, we show here for a case of one density, and we do for multiple densities, you'll see next. And the market penetration rate, as I mentioned, we're looking at the one in this study. So what we do is the following. We have a Monte Carlo simulation, and what it does is the following. For different distances, if you look at the x-axis here, you'll see different distances. For each distance, you have a center vehicle, receiver vehicle. And then, around that, we have, depending on the density, so for this density, 50 vehicles per kilometer, they're randomly placed within that space. When we do Monte Carlo simulation, what it's saying is, we do actually 1,000 Monte Carlo simulations for each case. So what that means is, they randomly place those vehicles around. So the center vehicle has a range of 500 meters, and then there's a receiver vehicle, then the rest of the vehicles are randomly placed. So 1,000 times we do this, and we are able to determine the probability of the communication happening. And as you can see, there is some, simulation actually shows some order here. And what we do here is we determine the nearest fit. And in this case, it's a Gaussian function. And there are other functions we have tried, but in this case, the fit is best here. And what we'll see is, based on that, this is the function that we adopt for the kernel function. Remember, that's the function that tells us whether the communication is likely to take place or not. And for different density levels, this curve fit, I'm sorry, I should have mentioned, there's alpha here, and then lambda. These alpha and lambdas are determined for different densities out here. Okay. We are looking in this case at 3 lanes. So we have close to from 0 to 480 density, 160 kilometers, vehicles per kilometer, that's the one. So 3 lanes, there's 480, so we're just showing up to this because we didn't have the space for the one. So you're seeing the curve fits for the various ones here. And based on that, we show that under a linear conjecture, and that I'll come to it in a little bit, the wave speed actually converges to an asymptotic speed. So there's some speed, and initially it's slower, and then it steadies itself at some point. And the linear conjecture is the following, and I'm not going to talk about this equation specifically. In the domain of epidemiology, they illustrate, because there's the nonlinear IDEs that are there, they illustrate that under certain conditions for them, the approximation, the linear approximation, which is where this term actually goes away, and you'll see here that the term associated with the E actually is invariant with time and space. So then they show that the solution that they obtain can be obtained in a more convenient way. So there's a negative nonlinear term that can be removed that allows them to solve the problem more easily. In our case, what we have found is, in order for that linear conjecture, so the linear conjecture is related to taking out this term, making this whole thing linear, because this term is constant term, and the rest of it is linear. Requires 2 things. The first one is the success rate of communication for informed vehicle is a non-increasing function of the number of vehicles. And that we saw through a kernel function. It's a non-increasing function with distance, and that's what we see in our case. The second point is that an informed vehicle has negligible influence to power. And that again, based on just that shape, but in the real world, that's true. So both of these hold, and because they're satisfied in our case as well, we are able to come up with a model that illustrates that. In the interest of time, I'm going to skip the actual derivation here, and I'm going to focus on this slide here, which illustrates the function that we use. So we tried different functions out here. In our context, we had this function here, if you see here. These are associated, alpha and lambda were associated with the shape. If you recollect, there's this table that we showed for different densities. And here, E is the density of equipped vehicles. Because it's homogeneous, that's why it was, I said it's invariant with space and time. If you recollect, I had shown that previously. It was E instead of E, X, comma, T. And then beta is the frequency of communication. So these are the mechanisms that go into determining the speed associated with the flow of information. So there's the traffic flow speed, there's the information flow speed, and together they tell us the speed at which the information flow propagation rate. So the traffic one is a very classical one. There's just the density speed relationship. That's what you're seeing here. It's constant for some time, the speed is constant for some time, then it starts sloping in a linear fashion. And in terms of numerical experiments, we have the following. So we look at a network with 30 kilometers. We break down into 2,000 cells. We have frequency of about 65 miles per hour. The time interval we look at is 0.5 seconds. Then we have a single lane. Market penetration rate is 0.5. So we say 50%. I mentioned that earlier. Those are on all the experiments. Then we have the critical jam density and the assumed frequency of communications. So with that, we use the case of a unidirectional. So we are just looking at a single highway in one direction, in which vehicles are moving. For that, we are able to come up with a closed form solution. Okay? So what we do here is we look at the closed form solution and the numerical. The numerical one is the exact one. I'll talk about that next. But the closed form solution in this case, you'll see in both the forward propagating wave and the backward propagating wave is very close to the numerical one. The fit, even in the context of the use of linear conjecture, even though it's approximate, the fit is really good out here. And as you go further in density, it becomes identical. So, and what you see here is that this is the traffic flow as a relationship between speed and density. That's just a standard relationship that we have seen before. And here what you'll see, this is the forward propagating wave, this is the backward propagating wave speed, and the forward one has higher speeds. And it's not surprising because the forward is in the direction of the movement of vehicles, the backward one is against the direction of movement of vehicles. Okay, so that's why the forward and the backward differ. The other thing you'll notice is that initially there is some increase and then it decreases. And the reason for that is initially the interference is not a key element because density of vehicles is sufficiently small that they're able to communicate. But at some point, interference starts coming into play, and then from then on, the ability to communicate decreases substantially. And that's the same whether you're looking at the forward or the backward propagating. And this is just an illustration of the best case scenario. If you look at this part, you'll see that when it's 400 or something, at that point, the closed form solution and the numerical solution, they're very close to each other. So it's simply saying 447 versus 447. So let's look at the second part here, which is the numerical solution, which is the exact one. So this is when we have heterogeneous, the more general case, where you have nonlinear IDEs. So in order to solve this nonlinear integral differential equation, we have an approach which uses two parts. First, there is a fast Fourier transform that we do, and then we use the Peeta method on the initial value problem to come up with the solution. So I'll skip again the process related to this and illustrate what we're able to find. So the numerical solution comes up using a finite difference equation method. So I'm going to skip the Fourier transform part, and this is the one related to the traffic side because there are two sides. There's the information side and the traffic side. And I want to show some results out here. So what happens in terms of the uniform traffic stream? So this is illustrating at different densities. As you can see, as density initially increases, things get better, then it gets worse because of interference. I mentioned that. And this is simply illustrating how the wave propagates. So on the x-axis you have distance in both directions from where the information has originated. So that's why you have backward and forward. And then the rate of informed vehicles. So you're seeing that out there. So you'll see that initially it starts out, we're showing for the K of 30, you're seeing what's happening, so slowly it spreads. And as you can see, it spreads faster for the forward rather than backward. Okay. Then it keeps spreading along with time. So, and then you see that it's occurring at different rates. And as you can see, as densities get higher, it gets worse because they're more compacted. In the backward direction, you're going against the flow, so you have even more penalty. Forward is getting affected by interference substantially. And here what you see is the asymptotic behavior. So what you see is the speed with time, what's happening. And the only reason you are seeing these kinks out here, in reality the kinks are simply a representation of the discretization. There's discretization that we do to solve this, okay, because we start with the initial continuous, it's integral, then we discretize it because we use finite difference equation and so on. That's why you see these kinks. Other than that, there's nothing out there to explain there. And the asymptotic speed is approach. So I said it starts slowly, then it reaches this asymptotic speed, and then it stays there. Now this is the case where you have two directional flow. Okay, so you have flow in both directions, and what's happening is the following. So we are very deliberate here. We are comparing it with the unidirectional case. So that's why it's saying analytical. The reason why we are saying analytical is it's a closed form case where you have two directions, unidirectional case. So even though we have the numerical solution, we were comparing it to the analytical one. Whereas the rest of them are all numerical, because this is the case where we cannot come to the closed form solution. And here you'll see that these are the traffic flows, the traffic speeds in both forward and backward propagating waves. But if you look at the performance of the forward and the backward in this, you'll see that the speeds are less than the one compared to the unidirectional one. And that's not surprising, because in the unidirectional case, you have only one direction of traffic flow and information is propagating in both directions. Here, we have some information that's propagating in both directions now. So there is the effect of the other direction as well showing up in terms of interference, and that's where it is in the wave speed. Okay? So that's the reason why when we have the two directional case, we cannot solve it in a closed form manner, it has to be numerical. We'll see that it's the envelope here is the single unidirectional two-lane case. So this is a case where I wanted to illustrate what happens when we have non-uniform traffic stream. So this is the application case where there's an accident. Let's say here an incident occurs at location A. So here we are looking at the distance, we are looking at time in this direction, and here you have the density of traffic. So this is all the traffic side. So that's where the traffic density contour. And what you're seeing here is an incident occurs at this point. This is the location where some vehicle perceives that and generates that information. And then what you start seeing here is because of that there's a backward propagating traffic wave. So as a result of that, what happens to the density? It becomes close to jam density here. So over time, you're having a lot of congestion upstream of the incident, and then downstream of the incident, there are hardly any vehicles. As a consequence, the density goes to zero. So that's what you're seeing. So there's a space-time diagram. And the point that I wanted to illustrate here is that there are consequences of that in terms of the informed vehicle density content. So here, the bottom figure is showing the density of informed vehicles. So you have distance, you have time. But see how you have A and C just to show the same reference points. But what happens is the following. Before the incident and so on, so what you have is there's a forward propagating traffic wave which is going at a certain speed because the density is uniform, 50 vehicles per lane. And then once the incident starts, you start seeing the heterogeneity in density showing up. So what happens? What happens out here? The speed of the information propagation goes almost to zero. That's not surprising, because what happens downstream of the incident, there's hardly any vehicle left, right? So there's sufficient space now that the ability to communicate doesn't exist. Then once the incident gets done, so the capacity is recovered, then vehicles start moving. So now they are in a very optimistic situation, so information flows at very high speed. Then at some point, because the density comes back to the normal case, once the perturbation is done, we again get back to the. So what you see here is a very important point, and that is assuming that information flows in a multi-hop context in an instantaneous manner simply is not meaningful when we look at the application domain. So that's the important point to mention here. And you'll see that this is the forward propagating wave. We can show it for the backward propagating wave. And if the thing happens here, how the information propagates, again, the same thing will happen. The backward propagating wave will slow down substantially as well. So in terms of contributions, first, we avoid this assumption of instantaneous multi-hop. So that's important because that's the real world when we have traffic flow. The second is we want to come up with a model that allows us to propagate a single unit of information using a broadcasting mechanism. So information just gets blasted out. So the third one is characterizing this communication by linking it to the communication constraint. So this is where we talk about the kernel function and so on. And it can allow us to then determine how we can get to what we call optimal information flow propagation. So what does that mean? That really depends on the application context. I'll talk about that in the next slide. And we are able to leverage mathematical theory that has been well developed in epidemiology and ecology as well to come up with a stochastic model for information flow propagation. And that allows us to come up with a macroscopic model for IFPW, and we'll see that this wave depends on vehicle density, which means this is where the traffic flow dynamics come into play. It depends on communication frequency, so we are talking about the information or communication network, so the interactions are illustrated here, and the shape of the communication kernel, which is dependent on both. We are able to come up with closed form solution. And closed form solution simply allows us to then design effective strategies because we can do it very efficiently computationally. We really get, if we can have closed form solutions, we can do a lot of things, and we are able to then come up with addressing what different designs will lead to. So we can actually do that. And naturally, when we talk about closed form solution, we are talking about a more idealized case when density is uniform. And there are many situations when that is true. The other thing is, when we have this ability to know where and how the information propagates, we can then link it to vehicle to infrastructure strategies. What that means is, where do we put transponders? Whether they're permanent or they're mobile transponders. Can we put them so that information that needs to reach certain locations can we reach that information within a certain threshold time? Why is that important? Suppose there's a massive accident somewhere, and let's say that that information is propagating to locations, in multiple directions, space and time. Now, you want to make sure that the information reaches people before they actually commit themselves to the facility that actually led them to just stay on that facility for a long time. I remember last time when I came here, in May,